Carminati's YouTube channel. I'm beyond excited to have you here today as we dive into a topic that feels like it's straight out of the future. In terms of quantum networking and the quantum internet, how can entanglement and teleportation be the dawn of unhackable communication? This subject is a game changer, and I can't wait to unpack it with you. If you're as fascinated by cutting-edge science as I am, please share your thoughts in the comments, suggest ideas for future videos, give this video a thumbs up, and hit that subscribe button to join our curious community. Let's embark on this journey into the quantum world together and explore how it could revolutionize the way we connect. What is quantum networking and why does it matter? Let's start with the big picture. How can quantum entanglement and teleportation pave the way for unhackable communication through quantum networking and the quantum internet? If you're new to this, don't worry. I'll guide you step by step, making it clear and engaging, even if you've never heard of quantum mechanics before. Quantum networking is the science of sending information using the strange rules of quantum mechanics, which governs tiny particles like photons, electrons, and atoms. Unlike regular networking, think Wi-Fi or fiber optic cables, quantum networking uses properties like entanglement and teleportation to share data in ways that classical systems can't match. The quantum internet, an ambitious goal, would link quantum computers, sensors, and devices globally, creating a network that's not just faster but potentially impossible to hack. Why does this excite scientists? Because today's internet, while amazing, has vulnerabilities. Hackers can intercept messages, crack passwords, and steal data. Quantum networking promises a new level of security by leveraging the quirky behavior of particles. To understand how, we need to dive into two key concepts: entanglement and quantum teleportation. These are the building blocks of unhackable communication, so let's explore them one at a time. Imagine two particles that share a special bond, like best friends who always know what the other is thinking, no matter how far apart they are. That's entanglement in a nutshell. When two particles entangle, their states link up. If you measure one particle's property, like its spin or polarization, the other particle instantly shows a matching or complementary property, even if it's halfway across the universe. Einstein called this spooky action at a distance, and it's the secret sauce behind quantum networking. How does entanglement make communication unhackable? Let's use a simple example. Suppose you and a friend want to share a secret message, but you're worried about eavesdroppers. In a quantum network, you could use entangled particles, say photons, to create a secure key, a kind of digital lock for your message. Here's how it works. You send one photon of an entangled pair to your friend and keep the other. Both of you measure your photons in a specific way, generating a string of numbers, your key. Because the photons are entangled, your measurements align perfectly, giving you identical keys. Now, you can encrypt your message with this key, and only your friend, with the matching key, can decrypt it. Here's the unhackable part. If a hacker tries to intercept your photon, quantum mechanics ruins their plan. Measuring a quantum particle changes its state, breaking the entanglement. You and your friend would notice the mismatch in your keys and know someone's snooping. This method, called quantum key distribution, QKD, ensures that any eavesdropping leaves a trace, making it a cornerstone of quantum security. Real-world example? In 2017, China used QKD to send secure messages via satellite over 1,200 kilometers. Banks and governments are already testing this tech to protect sensitive data. Entanglement doesn't just make communication secure, it makes it provably secure, something classical systems can't guarantee. Now, let's talk about quantum teleportation, another key player in the quantum internet. Don't picture beaming up like in Star Trek. Quantum teleportation doesn't move physical objects. Instead, it transfers the quantum state of a particle, like its spin or energy, from one place to another. This state is a kind of information, and teleporting it could help build a quantum network. Here's how it works, step by step. Imagine two researchers, Alice and Bob, want to teleport a photon state across a city. They start with a pair of entangled photons. Alice keeps one, Bob gets the other. Alice has a third photon, the one whose state she wants to teleport. She measures her photon alongside her entangled photon in a special way, creating a set of data, a recipe for the state. She sends this recipe to Bob through a regular channel, like email. Bob uses the recipe to tweak his entangled photon, making it match the state of Alice's original photon. The state has teleported! The original photon state, though, gets scrambled in the process. Why is this useful for a quantum internet? Teleportation lets you send quantum information, like the state of a qubit, the quantum version of a bit, between distant quantum computers or devices. Qubits are fragile. They lose their quantum properties if you try to copy them or send them through regular channels. Teleportation sidesteps this by transferring the state without physically moving the qubit, keeping it intact. For unhackable communication, teleportation amps up security. By teleporting quantum states, you can share encrypted data or extend QKD over long distances. In 2020, scientists teleported a qubit state across 44 kilometers of fiber optic cable, a big step toward a practical quantum internet. Combine teleportation with entanglement, and you've got a network where data moves securely and eavesdroppers get caught. Let's zoom out and dream big. A quantum internet would connect quantum devices worldwide, letting them share entangled particles and teleport quantum states. Unlike today's internet, which sends bits, zeros and ones, a quantum internet would send qubits, which can be 0, 1, or both at once thanks to superposition. This could unlock mind-blowing possibilities. Ultra-secure communication, quantum computers solving problems like climate modeling, and sensors detecting gravitational waves with unmatched precision. For unhackable communication, the quantum internet would rely on entanglement and teleportation at every step. Banks could transfer money without fear of cyber attacks. Governments could protect secrets with absolute confidence. Even everyday people could chat knowing their messages stay private. The catch? We're not there yet. Building a quantum internet requires stable quantum computers, reliable entanglement over long distances, and ways to store quantum states, called quantum memories. Progress is happening fast, though. In 2021, researchers in the Netherlands created a small quantum network linking 3 devices with entanglement. Companies like IBM and Google are building quantum computers, while startups are developing quantum repeaters to extend network range. It might take decades, but the quantum internet is coming, and it could redefine how we share information. This topic is more than cool science, it's a window into the future. Quantum networking challenges us to rethink security, technology, and even privacy. If you're intrigued, I encourage you to explore more. Read about quantum key distribution, watch talks on quantum computing, or check out experiments like China's satellite QKD. The more you learn, the more you'll see how quantum mechanics could shape our world. Start small, maybe a YouTube video or a beginner's book, and let your curiosity lead the way. What an incredible adventure. We've explored how entanglement and teleportation could make unhackable communication a reality through quantum networking and the quantum internet. From secure keys to teleporting qubits, this science pushes the boundaries of what's possible. I hope this inspires you to dig deeper into the quantum world. What do you think? Will the quantum internet change everything? Or is it too good to be true? Share your ideas in the comments. I read everyone. Suggest topics for our next video, give us a like, and subscribe to keep exploring with me. Thanks for watching, and I'll see you soon.